Good morning and welcome to our fifth lecture on advanced statistics, RMS618. This talk today is going to be on factor analysis. Now this is a correlational technique, so you're going to see a lot of, you're going to hear a lot of, hear a lot of terminology related to R and R squared, and you're going to see, and you will be familiar with this too. The purpose of factor analysis is to reduce variables in a data set. This is a data reduction method used to extract what we call common factors. We group variables with similar characteristics into factors, and we identify and measure latent constructs that explain the dependent variable. What this essentially can do is reduce, a 100-question questionnaire down into perhaps 5 or 6 common factors. So instead of having to ask 100 questions, we can essentially ask 5 or 6 questions to measure the same thing. We have this entity called factor structure, where our dependent variable is, the observed variable equals a function of common factors plus unique factors. A couple different types of factor analysis. The first one, and the one we're going to be focusing on today, we call exploratory factor analysis, or EFA. This also has another name. It's called principal components analysis, where we uncover this underlying factor structure using no prior theory. Okay, so we pretty much just have a hunch per se as to what the common factors are going to be. The second type of factor analysis we call confirmatory factor analysis, CFA. This has another name. It's also called structural equation modeling, okay, where we determine the number of factors loadings relative to theory. So we have actually a theoretical basis from prior literature that points us toward a particular factor structure. And we always do this before we do this. We'll not be covering this today. Okay, there's a lot of exploratory factor analysis out there, and let's see how this all works. Yep, we have some assumptions again. A linear relationship between variables. Like I said, this is a correlational technique, and we can assess that through scatter plots. Interval or near interval data. This is the same as saying continuous data. Okay. Some multicollinearity, but not too much. And we have a couple of measures to assess that. So we want, some relationships between the variables, but not too much, and adequate sample size. And we will determine that through this KMO test. We like to have sample sizes greater than 200, and so on, more than 10 observations per variable. We have some terminology that goes along with factor analysis. Components refer to factors, okay? We derive those from the correlation matrix. Communality. Now this is a term that's very similar to what we see in R squared. So like I said, you're going to see a lot of R and R squared types of definitions here, so to speak. The proportion of the variable's variance explained by the factor structure. This is also considered the reliability of a factor. And we know reliability relates to consistency of measurement. So it's the consistency of the factor. Okay. A new term, eigenvalue. This is the variance of a set of variables explained by a single factor. And we have some criteria for eigenvalues. Eigenvalues greater than 1. So when we do the extraction, which we'll see in a few minutes, we're looking for eigenvalues greater than 1. And the scree plot is nothing more than the visual representation of the eigenvalues, again used to decide how many factors should be extracted. And the factor loadings simply refer to the correlations between a factor and a variable. So as we see, lots of correlation and, coefficient of determination, R squared types of terminology here. And this is stuff you're all familiar with. Now we have a couple of steps in factor analysis, okay? Stage one we call factor extraction, where we're essentially calculating the factor loadings and examining the eigenvalues and the scree plots. And we will see this, in a minute when we get into examples. Stage two we call factor rotation. This is literally rotation of the axis to get a clear picture as to what's going on, okay? We statistically adjust results to make it easier for interpretation. So in this factor rotation, we use the most recommended technique called Varimax rotation. And all this is rotation, literally rotation of axis to get a clear picture as to what's going on in terms of factor loadings and relationships between variables. Let's look at an example. The researcher conducted a survey of faculty regarding the level of difficulty experienced when new technology is introduced to classroom. The objective is to use factor analysis to identify constructs that can explain the level of difficulty in using technology in the classroom. So we're going to be taken to the good old SPSS data view screen, okay? And we end up having 12 variables in the analysis. These variables are survey questions. Okay, question number 2, question number 5, question 10, and so on and so forth. What we're going to be doing is reducing these 12 questions to look at common factors. We're going to look at common factors. The SPSS analysis. Analyze data reduction factor. We bring the variables over. So we actually bring all 12 variables over into the variable screen. We probably going to take a look at some descriptives, and we'll click OK. Descriptives. We're going to do some basic univariate descriptives. We're going to look at the initial solution before the rotation, and we're going to run a couple of tests for assumptions, the KMO and the Bartlett's test of sphericity, and then we'll hit continue. We are going to do a principal components analysis. Remember, this is also the exploratory factor analysis, so it has two names. This EFA is also called PCA, principal components analysis. It's going to analyze the correlation matrix. We're going to look at the eigenvalues over 1. And we're going to look at the unrotated solution. And it's going to give us a little scree plot. So it's going to give us all sorts of interesting things, as we will see. Then when we do the rotation, we're going to click on the rotated solution. And like I said earlier, we're going to pick the Varimax rotation. It's kind of the Toyota Corolla of rotations, so to speak. Here's our descriptives. And as we see, we have our 12 variables. And just one interesting note, of course we have 126 observations for all the variables. Do we have homogeneity of variance here? Well, take a look at the data. We have very similar standard deviations. I would bet that we do have, homoscedasticity. It's just a guess, just an educated guess here. You also see the means are, fairly similar. Okay, let's see what's going on here further. Oh, our tests of assumptions. The KMO measure of sampling adequacy should be greater than 0.6. Now we see the 0.885 figure here. This is very similar to perhaps a little power analysis. This is telling us that we have enough research subjects in our sample to adequately conduct this factor analysis. Okay? So this KMO, so to speak, measures sampling adequacy, and we should have something, greater than 0.5 or 0.6. We do 0.885. Bartlett's test of sphericity. determines collinearity. Now this is actually a two-way chi-square. We see a very large chi-square estimate here. P is very, very, very small. A null hypothesis has been rejected. We have significant relationships between our variables here. Okay, strong relationship among variables. So we have, some collinearity in this situation. What we want. All right. Communalities. How much variance is explained by the factor structure? Now we see the initial communality, which is the perfect correlation, and then we see fairly high correlations in most of these variables. Okay, and what this essentially says is that we have lots of relationships going on here. We have lots of relationships going on here among these variables. And when we extract, we're going to see, what factors load on, one thing, what factors load on another thing. All right. The output. Now again, like I said, we're looking for eigenvalues greater than 1. The table summarizes the total variance explained by the factor analysis. Well, we have about 71.814% explained variation, and we have a two-factor solution. See, factor 1, eigenvalue greater than 1. Factor 2, eigenvalue greater than 1. Factor 1 explains about 56.191% of the variation. Factor 2 explains 15.623% of the variation to give a cumulative R squared, so to speak, of 71.814. So the two-factor model explains about 78.814% of the variation. And again, you see most of the loadings are, on factor 1. So the highest relationship is with factor 1. And we have a two-factor solution here. So essentially, most of these questions, most of the questions are actually just measuring two things. Measuring two things. And the scree plot, the visual representation of the eigenvalues. This just tells us, this is the graph. We see factor 1, 6 point something, factor 2, greater than 1. Criteria for deciding which components to extract. Eigenvalues greater than 1. We have the two-factor solution. Now we have our component matrix before rotation. So this is the unrotated solution. Now look at these loadings. Look at from about here up, we see very, very high relationships. And then, this is again before we've kind of rotated or, before we've shaken things up, all right? So this is before the rotation. Two components extracted, factor 1 and 2. Again, those eigenvalues were greater than 1. That's how we made that determination. Now we have the rotated loadings, the factor loadings after the rotation. And we see questions A1 through 8 loaded strongly, see, on factor 1. Questions A9 through 12 loaded strongly onto factor 2. So most of the questions loaded onto factor 1, and then 4 of them loaded onto factor 2, again the two-factor solution. Okay. The data were analyzed by principal components analysis with Varimax rotation. The KMO measure for sampling adequacy was 0.885, exceeding the 0.5 required value for factor analysis. Bartlett's test of sphericity was significant. Remember, this measures for collinearity. We had a significant chi-square. We came out with a two-factor solution. 2 components with an eigenvalue of greater than 1 were identified, and the scree plot also provided evidence of 2 components. Questions A1 through 8 loaded strongly onto factor 1, A9 through 12 loaded strongly onto factor 2. Okay. Now it wants us to do a little exercise. Conduct a factor analysis for the variables in resilience.save. These are survey questions measuring types of resilience. Okay? And it asks us about the assumption of collinearity, sample size, how many factors should be included based on the scree plot and the eigenvalues, how much total variance is explained by these factors, what variables loaded onto the factors. This is all stuff we did just previously. I think we can handle it. Let's see what's going on. Was the assumption of collinearity met? Well, let's take a look at Bartlett's test of sphericity. Again, we have another enormous chi-square with p less than 0.05. We have a significant chi-square here. So this assumption was satisfied. We have a collinear situation here. Was the assumption of adequate sample size met? We use the KMO test, Kaiser-Meyer-Olkin measure of sampling adequacy. This tells us that we have an adequate sample size because this particular figure is greater than 0.6. And again, this is very similar to a kind of a quasi-power analysis. You know, do we have enough subjects to attain significance? Well, in this case, yes. The scree plot. Well, let's take a look at it. How many factors should be included? Well, we know doggone well, we have 1 factor greater than 1. This one is greater than 1. I would bet we have another 2-factor solution. Let's see how it works out. How many factors should be included? Well, here we go again. We have 2 factors greater than 1. How much total variance is explained? Well, about 54.751 total variance is explained. Factor 1 explains about 29.688. Factor 2 explains about 25.113. I apologize for the some of these numbers don't come up real well, but I think we get the drift here. So again, we have another 2-factor solution. The factor loadings. What variables loaded onto the factors? Okay. Well, where do we have high correlations? Well, there's one here, one perhaps here, another one here, 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 maybe here, here, and here. Factor 2, where are the high correlations? Well, here's one. Maybe there, here, here, here. So as you see, all these little categories relate to resilience, following through with plans, proud of accomplishments, taking things in stride, handling many things at once, determination, self-discipline, laughing about things, believing in yourself, okay, looking for alternatives, energy, okay. So all these, all they're trying to do is extract common factors with this resilience survey. So again, we have another 2-factor solution. And we're looking at the rotated component matrix. All right. Summary. Okay, this is the last video in this little series. We've talked about correlation, simple linear regression, multiple regression, logistic regression, Manova-Mankova, a little bit about repeated measures, and then this last module 5 was on factor analysis. And again, if there are any questions, get on the discussion board and ask me a question. You can email me, you can call me at 248-495-4357. That concludes Module 5 on factor analysis. Have a great day.